Hello and welcome to section 4.12, where we're going to be talking a little bit about the energy of the different conformations that monosubstituted cyclohexanes can have. And when we say monosubstituted cyclohexanes, we mean cyclohexane molecules that have one substituent on the cyclohexane ring. Otherwise, they are all carbon-hydrogen bonds. So to draw this, an example of a monosubstituted cyclohexane, here's our wide V, our line that comes down near the V, parallel line, and the two lines that connect. So in a monosubstituted cyclohexane, we're talking about a case where perhaps there is a methyl in the axial position here. And remember that it's in the axial position because it is perpendicular to the carbon-carbon bond that makes up the seat of the chair. And if you are surprised by that, have a look at the section 4.11 video. Okay, so why don't we have a look at the Newman projection of this? We'll have a look at these two carbons. Here's our I. We're going to look right down these two carbons. We're going to look down the seat of this chair, much as we did in earlier sections. Okay, so if we did that, then let's just draw here. Let's just draw right here. These two carbons. And so to complete our chair structure, we can see that there's a carbon going down here in the front, and in the back, the carbon is going up. There we go. And remember that we don't see the bonds between the seat carbons in the chair, and we don't see the other carbons that make up the seat as well. Our orange CH3 is axial, so that means it's pointing straight up. And otherwise, we have a fairly normal hydrogen here. Two hydrogens on this side. Our hydrogens in the back. There we are. Okay. So if we label this orange one, again, as axial, right? Something strange happens, because before it was an earlier section, I believe it was section 4.10, we talked about the different conformations a cyclohexane could take, and we talked about how you could have different types of chairs, right? Because we said that the ring could undergo what's called a ring flip. Oh, those are weird looking. There we go. These are the conformation arrows, the equilibrium arrows. And we said that we could have a different type of chair. Oh, that one is not as good, is it? There we go. Where now the right side is pointing down and the left side is pointing up. And if we do that, funny enough, what once was axial now is equatorial, right? Because now it is parallel with the seat of the chair. And we can look at those same two carbons that we looked at before and see how that changes the Newman projection. So here, when we're writing a ring flip, we can say that it is the switching between axial and equatorial in a cyclohexane chair conformation. Okay, so we can draw our equilibrium arrows again with the Newman projection. And when we do that this time, you'll notice that it looks fairly different because of the ring flip. Because now on the left, oh, I forgot to draw my eye. Now on the left, that carbon is going up, and in the back, the carbon is going down. And also, as we said, the CH3 group that we were just talking about now becomes equatorial instead of axial. Here's our other hydrogens. And there we are. Oh, these are actually backwards. Excuse me. Yeah, there we are. Oh, yeah, see, these are backwards. That's why. Silly me. Sorry about that. There we go. And the hydrogens in the back as well. There we are. Okay, so when you have a ring flip, the substituents that are axial go equatorial, and the substituents that are equatorial go axial. So you could kind of imagine that it's an equilibrium between these two when you have a conformational switch like that. And you might ask yourself, well, why would that be? Why would you make a switch upon going to equatorial? And what we need to do actually is go right back to that original Newman projection that we just drew. So what I'm going to do is I'm going to redraw it down here so that we can better understand why a cyclohexane might want to even do a ring flip at all. There we are. And so it was going down in the front, and up in the back, and the CH3 was in the axial position. In a cyclohexane molecule, actually, there's a very special type of interaction that can happen that really affects which molecular conformer you see, or which chair conformation you see, and that is called the 1,3 diaxial interaction. And it arises because of the steric strain that comes between substituents in every 3 carbons away. So it'd be 1, 2, 3, 1, 2 in the back there, 3. So that means the substituents that I am now highlighting are in contact with each other in a steric way, much as the torsional strain and steric strain that we saw in section 4. I think it was 4.6, drawing Newman projections. The steric strain here says that because of the interactions between these groups, you're going to have a higher energy conformation than potentially if you were to do a chair flip or a ring flip. So a 1,3 diaxial interaction is a strain present in cyclohexane chair conformations that increases conformational energy. So how do you get rid of the 1,3 diaxial interactions? You do a ring flip. So we would just write in here, ring flip. There we are. And so now, if we redraw the Newman projection of a cyclohexane here, but again, reversing the direction, because the bottom, what was the bottom is now the top, and what was the top is now the bottom, then we see that the CH3 now becomes equatorial, while the rest of the hydrogens also change. And the CH3 should really be shown to be in the front. There we are. And so now, looking at these, the diaxial interactions, the 1,3 diaxial interactions that we just had previously because of the axial conformation of the previous CH3 is now gone, because the CH3 is in an equatorial position. No 1,3 diaxial interactions. And why is that? Because equatorial position. And that's pretty key, because there's a good example they show in your book where essentially if you have a choice between, oh, this is really not a good chair. Let's draw this slower. There's our V, and those two. There we go. So if you have a big substituent like this tertiary butyl group in the axial position, and you give the molecule a chance to equilibrate, that is, to find the lowest energy conformation, what will happen is that the molecule will choose to have that, that tertiary butyl group in an equatorial position almost all the time. And here we're showing that the equilibrium really lies on the right by the big arrow and the very small arrow. And if you were to compare the amounts of each, you would find this is greater than 99%, and this is less than 1%. Because the molecule's energetics are so much lower, the energy of the molecule is so much lower on the right. So this has been, also there's a nice table, 4.8, that shows you the diaxial interactions for different common substituents. And this has been section 4.12.